Hello students, welcome to the second lecture on the design of rolling element bearings. In the first part we have seen the basics of rolling element bearings such as the meaning, the classification, different types of bearings, the nomenclature, the specification, the advantages and disadvantages, the materials and the lubrication of the bearings. In the second part, we will have a look at the load capacities of the rolling contact bearings, the life rating of the bearings, and finally the procedure of designing or selecting a rolling contact bearing with the help of a example. Now the first parameter that is used to describe the capacity of a bearing is by its basic static capacity denoted by C0, or it is also called as basic static load rating. What is static load? It is the load carried by a non-rotating bearing. Static load is nothing but the load carried by a non-rotating bearing. Non-rotating bearing means either the inner race or the outer race will be rotating in a bearing. If both are stationary, then whatever the load that it takes is the static load. Then what is the static capacity? The basic static load rating is defined as the static radial load in case of radial ball or radial roller bearings, or axial load in case of the thrust ball or roller bearings, which corresponds to a total permanent deformation of the ball in a ball bearing or roller in case of a roller bearing and race at the most heavily stressed contact point, and the magnitude of the permanent deformation will be equal to 0.0001 times the diameter of the ball or the roller. Means if the total permanent deformation of either ball or roller and race, either outer race or inner race, is equal to 0.001 times the diameter of the ball or the roller, and that is called as the basic static load rating of a bearing, whether it is a radial ball bearing or radial roller bearing, or ball thrust bearing or roller thrust bearing. So it is the static radial load which deforms permanently the ball or the roller and race, and if its magnitude is equal to 0.001 times the diameter of the ball or roller, then it is the basic static load rating of a bearing. Second important parameter that is used to describe the capacity of a rolling element bearing is basic dynamic capacity denoted by capital C. Also it is called by the name basic dynamic load rating capacity. So dynamic means it is not necessary stationary, it is rotating. Member is rotating. Earlier it was static, stationary. Here it is dynamic, moving, rotating. So how it is defined? What is the basic dynamic capacity of a rolling element bearing? The basic dynamic load rating is defined as the constant stationary radial load in case of radial ball or roller bearings, or constant axial load in case of thrust ball or roller bearings, which a group of apparently identical bearings with the stationary outer ring, this is the outer ring which must be stationary, can endure for a rating life of 1 million revolutions, 10 to the power of 6 revolutions, which is approximately equivalent to operation of 500 hours at 33.3 rpm. So with only 10% of failure, means out of the 100 bearings tested, only 10% will fail and 90% will pass. So let us look again at the meaning of the basic dynamic load capacity. the basic dynamic load rating of a rolling element bearing is defined as the constant stationary radial load or constant axial load, as the case may be, which a group of apparently identical bearings with stationary outer ring can endure for a rating life of 1 million revolutions. So if a bearing with its outer ring stationary, and if it is capable of operating successfully up to 1 million revolutions, and that capacity is called as the basic dynamic load rating capacity. And if 100 bearings are chosen, and out of the 100 bearings, 90 bearings will operate at a speed of 33.3 rpm for 500. It is just an example. And 10% of the bearings will not reach 1 million revolutions. Before they reach this rating, they fail. That is the basic dynamic load rating capacity of the rolling element bearing. And third descriptor or parameter is dynamic equivalent load for rolling contact bearings. How it is defined? The dynamic equivalent load may be defined as the constant stationary radial load in case of radial ball or roller bearings, or axial load in case of thrust ball or roller bearings, which, if applied to a bearing with rotating inner ring and stationary outer ring, would give the same life as that which the bearing will attain under the actual conditions of load and rotation. Okay. Now here you can see there is radial load as well as the axial load. Now the combination of the axial load and the radial load means if you combine the radial load and the axial load with conditions of load and rotation conditions, then that gives you the equivalent load rating or equivalent load for rolling contact bearings. Here also, in the case of thrust bearings, there is the radial load and the axial load. The combination of these loads to get a single equivalent load is the equivalent dynamic load. The dynamic equivalent load for rolling element bearings is calculated by using this equation and can be found in Design Data Handbook by Mahadevan and Baladev, page 326, equation number 16.6. Now, what are these different notations? P is the dynamic equivalent load, X is the radial load factor, which can be obtained from the table 16.1, page 330 of Design Data Handbook by Mahadevan. Y is the thrust or axial load factor, again may be obtained from the same table of the data book. Fr, the radial load coming on the bearing. Fa, axial or the thrust load coming on the bearing. V, the rotation factor, again may be obtained from table 16.1 of the Design Data Handbook. And normally the value of V are like this. It is equal to 1 for all types of bearings when inner race is rotating, inner ring of the rotating bearing is rotating, and it is equal to 1 for self-aligning bearings when inner race is rotating, and it is equal to 1.2 for all types of bearings except self-aligning when inner race is stationary. So that means outer race is rotating and inner race is kept stationary. Either it is 1 or 1.2. So most of the time when the inner race is rotating, it is 1, and if the inner race is stationary, it is 1.2. Then another important parameter with respect to the rolling contact bearings is the rating life or life of a bearing. What is that? The life of an individual ball or roller bearing may be defined as the number of revolutions or the number of hours at some given constant speed which the bearing runs before the first evidence of the fatigue develops in the material of the one of the rings or any of the rolling elements. So, it is defined as the total number of revolutions if it is in terms of the number of revolutions or in terms of hours at a given constant speed before the first evidence of the fatigue develops in the material of one of the rings or the rolling elements. So we have seen how a rolling element bearing fares. So when a micropit is formed either in the outer race or the inner race or the roller or the ball, and if the size of that is equal to 0.0001 times the diameter of the ball or the roller, then we say that the bearing has failed. So here, what is the life of bearing? Life of bearing is nothing but before the first fatigue failure occurs, means the micropit occurs in any of the element of the bearing, and the number of revolutions or the number of hours completed before that first evidence of the fatigue is called as the life of the bearing. Also, it is defined as the rating life of a group of apparently identical ball or roller bearings is defined as the number of revolutions or hours at given constant speed that 90% of a group of bearings will complete or exceed before the first evidence of the fatigue develops. That means only 10% of a group of bearings fail due to fatigue and 90% will succeed in reaching that life in terms of revolutions or in terms of hours. Now this life of bearing is called as L10 life of bearing. Similarly, L50 life of bearing means 50% of the bearings are operational and 50% of the bearings fail. It is also called as the average life or the median life. And this is best represented in this graph where the x-axis is life of bearings and y-axis is the percentage of bearings in operation. Right. So L10 means here 90% of the bearings will succeed in completing this life and 10% of the bearing may fail to reach this life. And similarly, L50 or median life or average life of bearing means out of 100 bearings, 50% of the bearings will be able to reach this life and 50% of the bearings will fail before they reach this life. Okay? That is the meaning of the life of a bearing. And it is calculated by using these two simple equations. Ln, it is in terms of revolutions. N means number of revolutions, means at that particular number of millions of revolutions. So for ball bearings it is C by P raised to 3, and for roller bearings it is C by P raised to 10 by 3. Again, as usual, C is nothing but the basic dynamic capacity of the bearing in terms of newtons, and P the dynamic equivalent load on the bearing in terms of newtons, and Ln is life of bearing in terms of millions of revolutions. Now let us have a look at the procedure for designing a ball bearing. Actually, it is not the design procedure, but it is the procedure of selecting a suitable bearing for the given load conditions and running conditions. Now let us see how a bearing is chosen from the tables or catalog. with the help of this example. The example is like this: a simply supported shaft whose diameter is 50 millimeter, supported on bearings, carries a load of 10 kilonewton at its center. The axial load on the bearing is 3 kilonewton. The shaft speed is 1440 rpm. Select a bearing for 1000 hours of operation. So given our shaft diameter. Shaft diameter is nothing but the bore diameter of the bearing, 50 millimeter. Radial load at the center, 10 kilonewton. Radial load on each bearing, 10 divided by 2, 5 kilonewton. Axial load in this direction, 3 kilonewton. The speed of the shaft, 1440 rpm. Then the life of the bearing it has to run for is 1000 hours. Now let us calculate first the L10 life of the bearing, which is the total number of hours of operation, that is 1000 hours multiplied by 60, means this gives you total life in minutes. 1000 into 60 minutes is the operating life of the bearing, multiplied by the speed n, 1440, will give you total number of revolutions in millions. That means if you multiply, you get 86.4 million revolutions, or 86.4 into 10 to the power of 6 revolutions. Now, as we have seen in part 1, a suitable bearing when both radial load and axial loads are there, and when radial load is more compared to the axial load, the preferred bearing is single row deep groove ball bearing. Okay. Now for this application, where the radial load is 5 kilonewton, which is predominant compared to axial load, so hence a suitable bearing for this application is single row deep groove ball bearing. Now referring to table 16.9a, page 340 of the design data handbook by Mahadevan and Pallavi Reddy, and choosing a bearing having bore diameter of 50 millimeter, means bearing number 6210. 6 means deep groove ball bearing, 2 series, the light series, 10. If you multiply 10 by 5, 50 millimeter, which is equivalent to bore diameter of the bearing. For this bearing, and from the table we will get the value of C0, the static capacity of the bearing, as 20,595 Newton. So that is here in this page of the data book. 6210 bearing, small d the bore diameter, and the corresponding value of C0, static basic static capacity 20,595, and dynamic capacity is C value is 27,070 newtons. So for this bearing 6210, as a first trial you have chosen this. You see the bore diameter is 10, 50 millimeter, means if you multiply this 10 by 5 you will get this bore diameter. Now, as already calculated, the life is 86.4 million revolutions. Basic static capacity from the tables is 20,595 Newton, and then next step is to calculate this ratio FA by C0. Axial load is 3000 Newton divided by C0 is the, you get 0.1457. Now for this value of FA by C0, which is 0.1457, you have to get the value of E from the same table 16.1, page 330 of the design data book. Okay, so means for this value of FA by C0 equal to 0.1457, what is the value of E? Now look at this table 16.1. Here this is FA by C0, FA by C naught is 0.110, 0.170, but we have 0.1457. So to get the value of E, last column, for the value of FA by C naught equal to 0.1457, you have to carry out interpolation, right? So for 110 it is 0.30, for FA by C naught equal to 0.170 it is 0.34. So hence for value of FA by C naught equal to 0.1457, what is the value of E? So that is possible by interpolation. So by interpolation you will get the value of E as 0.324. Now also we have to calculate the ratio of axial load to radial load, FA by FR, which is 3000 by 5000, which is 0.6. Now if you compare this value of FA by FR with E, this value is greater than E, but that is 0.324. So hence for the single row bearings, when FA by FR, which is 0.6, and if it is greater than E, then from the tables we have to choose the value of X and Y. So which table? So already we have chosen here. So for the value FA by C naught of 0.1457 and FA by FR, when it is greater than E, you will get the value of X 0.56, and similarly when FA by FR is greater than E, the value of Y again we have to get by interpolation. So in between these two the value of Y lies. So the value of X for this ratio of FA by C naught, that is 0.1457, for FA by FR greater than E, value of X is 0.56, and what will the value of Y for FA by FR greater than E? Again by interpolation we have obtained those values. So X is 0.56 and Y is 1.356. Then with these values of FA, FR, X and Y, we will calculate the equivalent dynamic load P, XVFR plus Y into FA. So when the inner race is rotating, the value of V is 1. Let us assume that. After substituting all the values, you will get the equivalent dynamic load as 6868 Newton. Here, a point to be noted. If the loading conditions are given, like if a bearing is subjected to heavy shock loads or medium shock loads or light shock loads, then in that case this has to be multiplied by service factor CS, again which can be obtained from the data book. For different situations the service factors are given, and looking at the service conditions suitably, we choose the service factor and multiply this load by that service factor CS and get the total dynamic load. So here it is not necessary, as the shock conditions are not given, our service conditions are not given. Okay. Now, then after having calculated this equivalent dynamic load, the next step is to calculate basic load rating. That is dynamic load rating, basic dynamic load rating. C, which is equal to P into L raised to 1 by 3. So L we know 86.4 million revolutions, P is 6868 Newton, and you will get C as 30,317.22 Newtons. Now referring to the tables, for the value of C for the bearing which we have chosen 6210, for that bearing the catalog rating is 27,070 Newton. Now for this bearing 6210 to be suitable, this value, calculated value of C, must be less than this catalog rating. So hence, as calculated value of C which is 30,370 Newton, is greater than this, the catalog load rating. So hence this bearing is not suitable. Then what next? So you have to choose the next series of bearings. Instead of 6210, you have to choose 6310. 633 means medium series, right? So again repeat the entire procedure. We cannot change the diameter of the bore diameter of bearing. It has to be same 50 millimeter. So hence you have to choose the next series, medium series, deep blue ball bearing. Number is 6310. Again referring to the tables, we get value of C naught, static capacity as 34,720 Newton. Again using this value calculate the ratio of FA by C naught, which is 0.86, and again for this value of FA by C naught get the value of E from the tables, which is 0.028, and FA by FR is 0.6. again 0.6 is greater than this value of E 0.28, and hence the value of X for FA by FR greater than E is 0.56, and Y for value FA by FR greater than E from the tables, it is 1.55. So here it is, right? FA by FR greater than E, the value of Y. Here for the value of FA by C naught equal to 0.086, so it is 0.084. For the value of FA by C naught equal to 0.086, by interpolation you have to get what? The value of Y, but value of X will remain same as 0.56 for condition FA by FR greater than E. So by using these values we calculate the equivalent load, which is found to be 7,450 Newton. Then calculate the basic load rating C, that is dynamic load rating it is, and it is found to be 32,070 Newton. Now for this bearing 6310, in the table the value of C is 47,070 Newton. So as the calculated load rating is less than the catalog rate load rating, the bearing which you have chosen 6310 is suitable. Means this bearing is capable of taking this rated load, and it is able to complete how many million revolutions? 86.4 million revolutions. So friends, that is how the bearing is selected from the tables given the load conditions and the operating conditions of the bearing. Okay, CC. The value of C from the table is 47,070. So we are comparing this value of C 32,000 with this. This is less than this, hence the bearing selected, that is 6310, is suitable for the given load and operating conditions. Okay. Now alternatively, instead of comparing the dynamic load ratings C, you can compare the life ratings. So first you have chosen 6210 bearing, and for that you can calculate the life rating by using this equation C by P raised to 3. It comes out to be 61.23 million revolutions, which is less than the given or required number of revolutions. 86.4 million revolution is the required number of the bearing, but it is less than that, hence 6210 is not suitable. Then for the second case 6310 chosen, for that the value of C is 47,070 and equivalent load is 7450, and if you calculate L, it is 252.2 million revolutions, which is much greater than the required life of 86.4 million revolutions. So hence students, either you can compare the calculated dynamic rating and Kepler rating and decide the suitable bearing, or you can compare the life rating, required life and calculated life. That brings us to the end of the second part, and in third part we will meet with some more examples on the selection of rolling element bearings with the given load conditions and operating conditions.